Before I get into this one, I need to clarify the timing because I want to be straight with you rather than lean on manufactured urgency. This specific signal, or more precisely, the meaningful absence of one, was published by NASA on January 27th of this year, not 5 minutes ago. But it's a genuinely important result because it comes from one of the most closely watched planetary systems in the entire search for life beyond Earth. And it just ruled out several possibilities scientists had been hoping to confirm. This is the real story of what James Webb actually detected, and didn't detect, at TRAPPIST-1d, why the absence of a signal can be just as scientifically valuable as finding one, and what it means for the broader search happening across this entire 7-planet system right now. If you want accurate space reporting instead of exaggerated headlines, subscribe now because this investigation is still actively unfolding, one planet at a time. Let's start with why the TRAPPIST-1 system has become such an enormous focus of attention for astronomers searching for potentially habitable worlds, because it's a genuinely unusual system, even before you get into any of Webb's specific findings. TRAPPIST-1 is a small, cool, red dwarf star sitting roughly 40 light-years from Earth, orbited by 7 rocky, roughly Earth-sized planets, all packed into orbits considerably tighter than anything in our own solar system. Because red dwarfs like TRAPPIST-1 are the most common type of star in the entire galaxy, understanding whether planets orbiting this kind of star can actually hold onto a meaningful atmosphere carries implications reaching far beyond this single system. If red dwarf planets turn out to be capable of supporting real atmospheres despite the intense radiation these small active stars are known for, it would dramatically expand the number of potentially habitable worlds astronomers believe might exist throughout the Milky Way. If they can't, it would suggest genuinely Earth-like conditions might be considerably rarer across the galaxy than optimists have hoped. Michael Gillen, an astronomer at the University of Liège in Belgium who led the international team that originally discovered all 7 TRAPPIST-1 planets, explained the basic logic behind how Webb actually searches for evidence of an atmosphere on a planet like this. If a genuine atmosphere exists, heat absorbed on the side of the planet facing its star should get redistributed around to the planet's night side, the same basic process that keeps Earth's own nighttime temperatures from plunging to the same extremes found on airless worlds like our own moon. Without an atmosphere, there's essentially nothing available to carry that heat around the planet at all, meaning the redistribution of temperature between a planet's day side and night side becomes a genuine, measurable clue about whether an atmosphere is present, entirely independent of trying to directly detect any specific gas, if a story built on real, peer-reviewed research instead of manufactured urgency is the kind of thing you want more of. Drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. It helps to understand exactly why red dwarf stars like TRAPPIST-1 pose such a specific, well-documented threat to any atmosphere a nearby planet might otherwise hold on to. Because the danger isn't simply that these stars are dim. Red dwarfs are actually known for producing frequent, intense flares and bursts of high-energy radiation relative to their overall size, a pattern of stellar activity considerably more violent, proportionally, than what our own sun produces. Because TRAPPIST-1's 7 planets all orbit so closely to their star, considerably closer than Mercury orbits our own sun, every one of them sits directly in the path of that intense radiation environment. Over billions of years, that kind of sustained high-energy bombardment can gradually strip away a planet's atmosphere entirely, blasting lighter atmospheric molecules out into space faster than they can be replenished, a process astronomers refer to as atmospheric erosion. That's precisely the underlying concern driving Webb's entire TRAPPIST-1 observation campaign, testing directly, planet by planet, whether that theoretical erosion process has actually left every world in this system as an airless, barren rock, or whether some planets have found ways to hold on regardless. Webb has been working its way through the TRAPPIST-1 system planet by planet since shortly after it became operational, and the results so far have painted a genuinely complicated, evolving picture rather than a single, clean answer. The 2 innermost planets were investigated first. TRAPPIST-1b, the closest planet to its star, showed no evidence of carbon dioxide and appears to be, according to NASA's own summary of Webb's exoplanet research, most likely a bare rock without any significant atmosphere at all. Webb's observation of TRAPPIST-1b actually represented the first thermal emission measurement ever performed on any planet as small as Earth and as cool. As the rocky planets found in our own solar system, a genuine technical milestone in its own right, even though the result itself suggested a fairly barren world. TRAPPIST-1c, the next planet out, received a similar verdict through a separate independent study, with researchers measuring its dayside temperature and finding it too hot to be consistent with a thick carbon dioxide-rich atmosphere. effectively ruling out anything resembling a Venus-like world at that specific location in the system. If you found this systematic planet-by-planet approach as interesting as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It's worth understanding the specific observational technique researchers use to reach these conclusions about TRAPPIST-1, B, and C, because it's slightly different from the transit method covered for other exoplanet atmosphere detections, and the distinction matters for understanding exactly what these results do and don't tell us. Rather than watching starlight filter through a planet's atmosphere during a transit, researchers studying the two innermost TRAPPIST-1 planets used a technique called secondary eclipse observation, measuring the combined light of the star and planet together, then measuring it again as the planet passes directly behind its star and briefly disappears from view. The difference between those two measurements reveals the planet's own thermal emission, essentially how much heat it's radiating on its own, which in turn reveals its dayside temperature. A planet with a genuine atmosphere capable of redistributing heat around to its night side will show a cooler dayside temperature than a bare rock with no atmosphere at all, since a bare rock has no mechanism to spread that absorbed heat anywhere else, causing it to run hotter directly under its star's glare. That's precisely the measurement that allowed researchers to determine TRAPPIST-1C's dayside temperature was too high to be consistent with a thick, heat-redistributing carbon dioxide atmosphere, and it's a technique specifically suited to rocky planets sitting close enough to their star to produce a detectable thermal signal in the first place. That brings us to TRAPPIST-1D, the planet at the center of the actual headline this video is built around, and the results here turned out to be genuinely more ambiguous than the cleaner verdicts reached for planets B and C. According to NASA's January 2026 announcement, Webb's near-infrared spectrograph did not detect molecules commonly associated with Earth's own atmosphere, including water, methane, or carbon dioxide, in the light coming from TRAPPIST-1D. Red. In isolation, that might sound like a simple, disappointing non-detection, another rocky planet joining B and C on the list of apparently barren worlds, but the actual scientific interpretation turned out to be considerably more nuanced than that, and it's worth walking through exactly why. Unlike the secondary eclipse method used for the two innermost planets, the TRAPPIST-1D and E observations came from a dedicated research program astronomers named DREAMS, using Webb's near-infrared spectrograph and transmission spectroscopy mode, the same basic transit-based technique used to study planets like WASP-39b, watching starlight filter directly through a planet's atmosphere as it crosses in front of its star. That approach is generally better suited to searching for the presence of specific molecules directly, rather than simply establishing an overall temperature the way the secondary eclipse method does, which is part of why researchers were able to specifically rule out water, methane, and carbon dioxide for TRAPPIST-1D, even while remaining genuinely uncertain about whether some other, thinner or cloud-obscured atmosphere might still be present. Different planets in the same system, in other words, have actually been investigated, using genuinely different observational techniques, each suited to answering slightly different questions, which is part of why the overall picture across all 7 worlds still hasn't converged into one single consistent story. Louis-Philippe Piollet-Gorrieb, the researcher who led this specific analysis, laid out several genuinely distinct possibilities that remain consistent with exactly what Webb observed, and none of them can currently be ruled out based on the data collected so far. TRAPPIST-1D could have an extremely thin atmosphere, similar in overall character to Mars, present but faint enough that Webb's current observations simply weren't sensitive enough to detect it clearly. Alternatively, the planet could be covered by very thick, high-altitude clouds, obscuring whatever atmosphere might exist underneath them from Webb's view entirely, a scenario closer to how the thick cloud layer shrouding Venus makes that planet's actual surface conditions difficult to directly observe from space. Or, as a third genuine possibility, TRAPPIST-1D really could be a barren rock with no atmosphere at all, the same basic conclusion already reached for its 2 inner neighbors. Piollet-Gorrieb was explicit that the current data simply can't distinguish between these 3 scenarios yet, a genuinely honest acknowledgement of the real limits of what a single set of observations can actually establish. That kind of careful, hedged conclusion might sound less exciting than a clean, definitive answer, but it actually reflects exactly how this entire field of research is supposed to work when it's being done responsibly. Detecting the complete absence of an atmosphere is a comparatively straightforward result to establish with confidence, since it simply requires observations sensitive enough to notice that nothing is present. Distinguishing between a thin atmosphere, a cloud-obscured thicker one, and no atmosphere at all requires considerably more sensitive follow-up observations, ideally covering additional wavelength ranges and gathering data across multiple separate transits, before researchers can responsibly settle on one specific explanation over the others. It's worth understanding that TRAPPIST-1d isn't actually the planet most people watching this particular system are most excited about anyway, because that distinction generally goes to TRAPPIST-1e, widely considered the single most promising candidate for habitability among all 7 planets in the system, sitting comfortably within the star's habitable zone. Webb's investigation of TRAPPIST-1e, described in research published in 2025, found no strong evidence for carbon dioxide in its atmosphere, ruling out a thick Venus or Mars-style atmosphere dominated by that specific gas. But researchers were careful to note that current observations simply aren't yet sensitive enough to confirm or rule out the presence of a considerably thinner atmosphere on that planet either. Essentially, the same fundamental limitation encountered with TRAPPIST-1d applied to the system's single most scientifically important target. Even TRAPPIST-1b, the planet with what initially looked like the clearest, most settled verdict of bare rock and no atmosphere, has recently seen that conclusion genuinely complicated by fresh analysis. A more recent look at Webb's existing data on TRAPPIST-1b suggested the planet might actually possess a hazy, carbon dioxide-rich atmosphere after all, an interpretation directly in tension with the planet's earlier bare rock classification. That same fresh analysis also turned up an unexpectedly high surface temperature reading for the planet, raising the genuinely intriguing alternative possibility that TRAPPIST-1b might be volcanically active, with ongoing eruptions potentially replenishing an atmosphere that would otherwise be expected to get stripped away entirely by the intense radiation streaming from its host star. That's precisely the kind of reversal that illustrates how genuinely difficult and iterative this entire research process actually is. Planet initially written off as barren, getting pulled back into active scientific debate as researchers continue refining their analysis of the exact same underlying data. It's worth noting exactly where this leaves the full 7-planet picture, because Webb's TRAPPIST-1 campaign is still very much a work in progress rather than a completed survey. With B, C, D, and E now investigated to varying degrees of certainty, the system's 3 outermost planets, F, G, and H, sitting at greater distances from their star where any surviving atmosphere would face a somewhat less punishing radiation environment, remain considerably less thoroughly characterized. Researchers have specifically flagged those outer planets as important remaining targets since their greater distance from TRAPPIST-1 could plausibly make them more likely candidates for retaining a genuine atmosphere than their more heavily irradiated inner neighbors, offering a potentially cleaner test case once Webb's limited, heavily competed for observing time allows for the kind of extended follow-up these fainter, more distant signals require. So why does any of this actually matter, given how consistently uncertain and hedged these individual planet-by-planet results keep turning out to be? Because TRAPPIST-1 represents the single best opportunity currently available anywhere in the galaxy to systematically test a genuinely fundamental question about small, red dwarf stars and the planets orbiting them. Whether the intense radiation environment surrounding these extremely common stars strips away planetary atmospheres entirely, or whether some planets, under the right specific conditions, manage to hold onto or continuously replenish an atmosphere despite that hostile environment. Testing that question on a single planet tells you comparatively little. Testing it systematically across 7 planets, all orbiting the exact same star at different distances and under different specific conditions, gives researchers something considerably more valuable, an actual comparative data set, letting them study how atmospheric survival changes as a function of distance from a red dwarf star, using 7 genuinely comparable natural experiments happening within the same single system. It's worth being clear about what these accumulated TRAPPIST-1 results do and don't tell us about the broader search for habitable worlds around red dwarf stars generally, because a single system, however well studied, can't settle a galaxy-wide question entirely on its own. What the TRAPPIST-1 results so far genuinely suggest is that atmospheric survival around a small active red dwarf star is neither guaranteed nor impossible, but instead depends on a genuinely complex combination of factors: a planet's specific distance from its star, its likely composition, whether ongoing volcanic or geological activity might be actively replenishing atmospheric gases, and how much high-energy radiation a given red dwarf star happens to produce over its lifetime. That's a considerably more complicated, more scientifically interesting picture than a simple yes or no answer would have been, and it's exactly the kind of nuanced understanding that continued, careful planet-by-planet investigation like Webb's ongoing TRAPPIST-1 campaign is specifically designed to build. There's a specific technical complication unique to observing planets around a star like TRAPPIST-1, that's worth understanding, because it adds another genuine layer of difficulty to every single result covered in this video. TRAPPIST-1, like most red dwarf stars, is magnetically active, covered in star spots, relatively cooler, darker regions on its surface, similar in nature to sunspots on our own sun, but considerably more extensive and more variable, given how active these small stars tend to be. Those star spots can actually contaminate the exact same light signal researchers are trying to use to study a planet's atmosphere, a phenomenon astronomers specifically refer to as stellar contamination, since light passing near or through regions of the star affected by these spots can introduce false signals that mimic the presence of specific molecules in a planet's atmosphere or mask real ones that are actually there. Every research team working on the TRAPPIST-1 system has to carefully model and account for that stellar contamination before drawing any conclusions about the planets themselves, an additional layer of analysis that doesn't exist in the same way. When studying planets around quieter, less magnetically active stars, and one more reason why definitively settling the atmospheric status of any single TRAPPIST-1 planet has taken considerably longer than researchers might have hoped when Webb's observations of the system first began. So, what does all of this actually add up to? James Webb's investigation of TRAPPIST-1, D, published in January of this year, did not detect water, or methane, or carbon dioxide in the planet's atmosphere, a result that, taken on its own, might sound like a simple non-discovery. But the actual scientific interpretation remains genuinely open, with researchers specifically unable to distinguish between a thin, Mars-like atmosphere, a thick atmosphere obscured entirely by high clouds, or no atmosphere at all, based on the sensitivity of current observations. That ambiguity sits within a much larger, still unfolding investigation across the entire seven-planet TRAPPIST-1 system, one that's already produced genuine surprises, including a fresh reanalysis suggesting that previously written off TRAPPIST-1b might actually host a hazy, volcanically replenished atmosphere after all. It's also worth being honest about the scale of what's actually riding on the system's results, because TRAPPIST-1 isn't simply one interesting planetary system among many. Given how common red dwarf stars are throughout the Milky Way, outnumbering sun-like stars by a considerable margin, whatever general pattern eventually emerges from TRAPPIST-1's 7 planets, whether their atmospheres tend to survive, tend to erode away entirely, or depend heavily on specific factors like volcanic replenishment, carries implications for estimating how many potentially habitable worlds might actually exist across the entire galaxy. A galaxy where red dwarf planets reliably lose their atmospheres to stellar radiation looks considerably less promising for the search for life than one where at least some fraction of these planets manage to hold on, whether through favorable distance, geological activity, or some combination of factors researchers haven't fully identified yet. That's the real weight sitting behind every individual, carefully hedged result covered in this video. Not a single dramatic answer, but a slow, planet-by-planet accumulation of evidence that will eventually help answer one of the largest open questions in the entire search for life beyond Earth. There's a broader point worth carrying away from this specific story, one that applies well beyond TRAPPIST-1 itself. The search for a genuinely habitable world beyond our solar system was never going to resolve itself in a single dramatic announcement, and TRAPPIST-1D's ambiguous result is a fairly representative example of what that search actually looks like in practice: careful, incremental, frequently inconclusive, and occasionally reversed entirely as better data or better analysis becomes available. That's not a disappointing way for this story to unfold. It's simply what rigorous science looks like when it's being done honestly, one planet, one observation, and one carefully qualified conclusion at a time. If stories like this, the accurate and appropriately hedged version rather than a manufactured breaking news moment, are what you come here for, subscribe to this channel and turn on notifications, because Webb's TRAPPIST-1 campaign is still actively working through the remaining planets in the system, and there's a very real chance the next result changes this picture considerably. Thanks for watching, and I'll see you in the next one.